Welcome to The Explainer. Okay, today we're jumping into a really cool puzzle. How do you find the absolute highest point of a curve in the fastest, smartest way possible? We're going to be looking at a seriously powerful algorithm called ternary search to figure that out. Let's dive in.
All right, picture this. You're standing at the bottom of a huge mountain range, and your mission is to find the very top. Not just any high point, but that one single highest peak.
But here's the kicker. You want to be smart about it. You can't just walk the entire length of the range checking every single foot of elevation. That would take forever, right? We need a much better strategy.
And that little challenge, that's exactly the kind of problem that this super elegant algorithm called ternary search was designed to solve. It's all about finding the best spot without all the busy work.
So to be super clear, we're not just looking for any old value. We are on a hunt for the peak, that one specific point where things reach their absolute maximum before they start to head back down again.
So how in the world does it work? Well, what's so cool about ternary search is how it cleverly whittles down the possibilities. Now, if you've heard of binary search, you know it splits its search area in half. Ternary search does something a little different, and in a way, a little more clever.
Instead of just one midpoint, it drops two flags or test points right inside your search area. Think of one at the 1/3 mark and another at the 2/3 mark. These 2 points are the key. They give you a feel for the lay of the land, the shape of the hill.
And by simply comparing the height at these two spots, you get a massive clue. Is the ground between them sloping up, or is it sloping down? The answer to that one simple question, well, that's the engine that drives this whole algorithm.
Right, so that comparison, that is the absolute core of how this works. Because based on that one single piece of information, you get to make a really powerful decision that just obliterates a huge chunk of your search zone. Let's see exactly how that plays out.
So the process kicks off by defining your whole landscape, from a starting point A all the way to an ending point B. Then it calculates those two special midpoints, M1 and M2, which slice that entire range into 3 perfectly equal sections.
Okay, now for the magic trick. You check the heights at your 2 flags. Let's say the height at M2 is greater than the height at M1. Well, that tells us the slope is still going up. The peak has to be somewhere to the right of M1. So we can just, poof, throw away that entire first third of our map. Gone. We know the peak isn't there. Now, what if M1 is higher? It's the exact opposite. The peak has to be somewhere to the left of M2, so we can chuck that entire last third.
And you just do that again and again and again. Every single time, you're shrinking the search area by 1/3. You're basically cornering the peak, giving it less and less room to hide until you've zeroed right in on the solution.
Okay, so this all sounds amazing, right? But there is one really important rule here. A catch, if you will. You can't just throw this algorithm at any random set of data and expect it to work. The function has to be what we call unimodal. All that really means is that it only has one peak. Just one. Think of a single perfect hill. It goes strictly up, hits its maximum, and then strictly goes down. If you have a crazy mountain range with lots of different peaks and valleys, the algorithm can get confused. It might see a small local slope going down and mistakenly throw away the whole section that contains the true highest peak. And this, right here, is probably the biggest misconception out there. Let me be clear. Ternary search is not a replacement for binary search. They solve completely different problems. Binary search finds a specific item in a sorted list. Ternary search finds the highest value on a hill-shaped curve. Totally different tools for totally different jobs.
So, why do we even bother with all these rules? What's the big payoff? Well, it all comes down to one thing: absolutely incredible efficiency. In computer science terms, the algorithm's speed is O of log n, or logarithmic time. But what does that actually mean for you and me? It means it is ridiculously fast. For example, finding the peak in a range of 1,000 items might take, 7 or 8 steps? But in a range of 1,000,000 items, it only takes about 14 steps. You can make the problem 1,000 times bigger, and the work barely even increases. It's insane. And you'll see this powerful idea pop up all over the place. It's a huge favorite in things like competitive programming contests, where every millisecond counts. It's also fantastic for scientific modeling and pretty much any optimization problem where you know there's a single best answer hiding at the top of a curve.
Yeah, at its heart, it's a classic optimization technique. And the key phrase here is derivative free. See, normally you might use calculus to find the peak of a curve, right? But that requires you to have a nice, neat mathematical formula. Ternary search doesn't need one. It finds the peak just by testing points and seeing what happens, which is incredibly useful for complex, messy, real-world problems.
So the core takeaway is this. By cleverly using 2 test points to understand the shape of a problem, you can eliminate huge sections of your search and find that peak with incredible speed. It's a powerful reminder that sometimes the best strategy can make even the biggest mountains seem easy to climb. So the question is, what hidden peaks could you find?